everybody. Can you hear me there?
Yes.
Probably, yeah. So, welcome to one of our first, let's say, distinguished lectures or distinguished seminars by the Network Science Institute here. It's very nice to see a lot of friendly faces and a lot of new faces and some non-friendly faces. You are recorded, remember that. Anyway, so let's start. It's my great honor to introduce our distinguished speaker, Alain Barra, who's one of the leading figures in the field of complex systems and network science, one of the founding fathers. There are others in the room, but we're going to talk about them during the beers. So Alain obtained his PhD in theoretical physics from the University of Paris, working in 1996, working with Marc Mézard in outer equilibrium physics. Then he went on to Trieste at the ICTP, which is one of the best theoretical physics places in Italy, well, in the world, and it's in Italy. And then joined the CNRS as a junior researcher, 98, and went to stay and spent a lot of time in Paris until he joined the Centre de Physique Théorique in Marseille, and then became first a research director, and then a deputy director, and now the director of the whole thing. So even just the fact that he's here with us today is a great honor because he's very, very busy. Now, beyond the role in Marseille, he's also had a bunch of positions, including he was a research associate or scientist at ISI Foundation in Turin, which is where I met him. And this was actually one of the highlights of my career because it's where he took a skimpy PhD student and made him into a researcher and approximation of adult, and actually eventually led me here. He's also been a specially appointed professor at the Tokyo Tech World Research Hub Initiatives, a very long name, from 2019 to 2022. And in his free time, he actually likes learning Japanese and cats. This is like a gem for you. Research interests, very vast. They encompass basically complex temporal networks, a bunch of interdisciplinary applications from epidemiology, computational social science, social systems in themselves. More recently, we've been working about higher order systems together, so it's very, very, very wide. But I think one of the highlights is that he's a co-founder of the Social Pattern Collaboration, which is one of the largest and most interesting collaborations dedicated to collecting micro contact, face-to-face contacts for the interest of micro epidemic modeling, understanding how, for example, an epidemic will spread in an environment like this, on top of coordination of people and so on and on. And it's actually one of the data sets that has been used the most, at least in our community. He's made large contribution, more than 150 scientific publications, and he has written, co-authored the book, Dynamical Processes on Complex Networks, which I assume everybody in this room has read, and if you have not, go read it now, and that's basically one of the foundational texts in the field. I discovered doing my research before this that he also has won a bunch of prizes, awards that I didn't know about, particularly the Paul Langevin Prize from the French Physical Society, but then there is in 2009, but there is another one which I love, which is Jeune Chercheur from the Festival de Science and de Sciences et Technologies in Marseille, 2011, so young researcher in 2011. And then, of course, he's been like outstanding referee for the APS and so on. He's an editor at the Physical Review Letters and a bunch of other honors and services to the community, including being vice president of the Complex Systems Society, board member of the Network Science Society, and a few other things that I don't know about, but I'm pretty sure. So please join me in welcoming who I came to call a mentor and a friend, Alain Barra, whose work in complex system continues today to expand the knowledge of our understanding of how this world is made up.
Thank you so much for the introduction. I'd say now we can go and have a beer. And yeah, so actually, in fact, I have become 1 year ago director of this laboratory in Marseille. And actually being here is for me a fantastic opportunity because I'm a bit, remote from usual bureaucracy and hassles, and I can enjoy scientific discussions, and that's really so a fantastic week to in this first. It's probably my best week in the last few months. So today, indeed, I want to talk to you about a bunch of research that we've developed with, of course, a number of other researchers, of colleagues, postdocs, and students over the last years. And so for this talk, I decided to try to take a relatively broad view on things I've been doing in the last 10, 15 years. So there will be a bunch of stuff. Hopefully it won't be too long, but I might have to skip a few stuff at the end. And the point is that there's a kind of a thread in a number of my works, which is about data and how to feed data into models of epidemic spreading, and how to understand how this data and these models can help us for obtaining insights that can be actionable. And so not only purely theoretical, of course I've done a number of purely theoretical works, but then working with epidemiologists, working globally with other fields, enriches your perspective a lot, and you want also to have some ideas about more applied, more actionable points. So when we want to model epidemic processes, I like to separate into two big issues. And the first one, on which I will not focus at all, is how we describe the evolution of the disease within the host, so within our cells, how we go from being healthy to sick, a bit sick, a lot sick, and then slightly better, and then we recover. So typically, we use very, very simplified simplifying assumptions, like the famous SIR or SIS model, in which the state of the host, of the individual who is sick, is discretized. You are first healthy, then you are sick, you are infectious, and then you are again susceptible, or maybe you are recovered, and then you do not participate to the spread anymore. And there you completely neglect all the differences, the heterogeneities, that can be due to many factors, including age, gender, but also socioeconomic conditions, that influence actually how long we will remain sick, for instance, how easily we recover, etc. And so the state of the individuals can change spontaneously for recovery, typically. Well, spontaneously can be helped by medicine, of course, by drugs. But most importantly, the state changes when one becomes infectious by contagion from other individuals through typically pairwise interactions. And so the second very important part is how do we represent these interactions in the population of interest? What is the structure? Who is in contact with whom? And that is because on these interactions, the contagion events can occur. So the representation in a population of this structure of interaction can vary from extremely simplified versions to very detailed. And I will try to cover a bit this range of possibilities. And in each representation, we will have to understand, to have a certain amount or type of data at our disposal to be able to fit the models. So that's a picture that was created by Victoria Colitza, I think, in an old paper of ours, and which tried to schematize a bit this series of possible representations. So from very simple homogeneous mixing or mean field, in which potentially everybody can interact with anybody else, to agent-based models that become extremely realistic, that try to mimic a whole population with people who have households, move to work, move to put their children at school, go to work, etc. But then you lose, obviously, in simplicity and in transparency of the models. And in the middle, you have also a lot of possibilities, like a social structure in which you group individuals, for instance, by age. You have the contact network, I will talk about that. And you have also multi-scale models in which you take into account the fact that people move, for instance, between locations. And the type of data, as I was saying, and the amount of data will vary a lot. So if you just have an average mean field representation, you just need to know more or less how many people you are in contact with on average. If you have an agent-based model, you will need very detailed data about the demography, about the occupation, about the mobility, and you will need to make also some hypotheses on how people interact when they are located in the same area, in the same building, for instance. In contact network, we'll talk about that. You need the structure of the contact network. When you use a partially homogeneous mixing but with edge structure, you need contact matrices and demography. I will talk about that. And when you have multi-scale models, of course, the most important quantity will be the fluxes of passengers. So let me review a bit. And of course, each type of modeling will actually correspond to a certain scale at which we try to see and understand the propagation. So starting from the global scale, the planetary scale, the world scale, what you use typically is a multi-level description with meta-population models in which you look at geographical areas, which are hopefully not too big, and like, for instance, cities, and inside the cities, you will make a simplifying assumption of a homogeneous mixing, but then you will try to take into account very, as well as possible, the mobility of individuals between the different patches, the different populations. So the data you will need there will be the city populations, how many individuals you have in each geographical areas, and you will need the fluxes of passengers between these geographical areas. And then inside each city, you can model an SIR, but you can model something more complex. That was the example of SARS. And you do this modelization in which people interact in a city, then they travel and they can bring the disease to another city. And what I would like to draw your attention to the references there, in which you see that this approach is absolutely not new. It's been there for a very long time. But when we started working on epidemics in the years 2000, 2005, what was new was the access to data. Basically, these first papers, they could use only very limited data, only on like the 50 largest airports in the world. They had limited access to data about fluxes of passengers, and they had obviously limited access to computers to deal with this data and to perform, to implement models on the computers. What has really changed is that now we have descriptive data at very detailed level about population densities, for instance, also about socioeconomic data, about mobility at various scales, about both commuting and long range. And we have the ability to write code that can integrate thousands of differential equations at the same time. So we, at that time, we built first a very simplified model with Mark Barthelemy, Vittorio Colizza, and Alessandro Vespignani, to show first that it was possible, to show how data could allow us to bring forward this kind of modeling. And then we also did some simulation, some study of scenarios of, at that time we were thinking about pandemic influenza. There was the avian flu, there was various threats, and one was thinking obviously about influenza-like diseases. And then, and probably you all know that, Alessandro Vespignani and Vittorio Colizza pushed this already much further with their respective teams and developed this global epidemic mobility model in which they go to a much more detailed, fine-grained resolution of the population, of the mobility, both short range and long range, and they have developed this very impressive simulation tool and framework that was used in various cases. It was used during H1N1, it was used during the Zika, it was used during Ebola, and obviously recently it was used also during the COVID pandemic, in which it helped, for instance, understand not only the risk of importation in early 2020, the risk of importation to Europe, but it also helped understand very soon, if you look at the dates, that most of the cases that were imported were not detected, and that was February 2020, and if you remember at that time, most people were kind of scrambling to understand. And it also helped, that's another paper by the team of Alessandro, the effect of the travel restrictions that were implemented at that time, if you remember, in China, only in Wuhan. And they were showing basically that it was too late in some sense because it had already spread to neighboring areas. So this kind of framework has shown to be extremely powerful, extremely useful to understand the spread at, let's say, a global level and to understand the threats that can come when a pandemic starts. However, then you want to go to smaller scales, obviously to understand a bit what's happening inside the city, for instance, and not only, okay, there are cases on the city, but how is it spreading now? And so what are the descriptions that you want to develop at this local scale? What kind of data do we have? What kind of models can they feed? And here, the kind of data that we will be able to rely on, and that, once again, have been used a lot during the COVID pandemic, are surveys. And it turns out that already in 2008, people had made an immense effort of gathering data through surveys in many European countries, asking people to remember with whom they had met a specific day, for instance, in which context, and what age the other person had, etc. And that allows for each individual who responded to have an idea of their ego network, meaning the set of people they had interacted with in a specific day. But you don't have then the structure of the global network, because you have basically a sampling of the participation of the population, which is a number of people who tell you information on the other people they have met. You don't have a network. What you have, and it's another extremely useful kind of data, are contact matrices that give you, for each age bracket, let's say, depending on the data, you can make age bracket of a few years, with how many other person of each other age bracket you have met. And here you see that you have the diagonals telling you that people tend to interact with people of the same age, but you have also some out of diagonal correspond typically to parents with their children. And you can have this kind of data in different countries. You can have separated by context in the household, in the work, in the schools, at work, etc. And this is the kind of data that you can feed into models. More recently, just want to attract your attention to this more recent database that has been collected during COVID-19, and so which is data that is much more recent, but that is influenced potentially by COVID. And it has been, so that's not using this comics data set, but this similar data has been used in this paper to compare what was happening, what would have happened with the contacts before the pandemic, and what happened when there was the outbreak with very strong restrictions on mobility on contacts. And so in the bottom, you see basically what would have been the R0 or the outbreak size for a situation with restrictions, with respect to what it could have been for a situation without restriction, showing that basically the restrictions were able, in this kind of modeling approaches, in which you just take into account this contact matrix, and to basically put the R0 lower than, to values lower than 1, and then to extinguish the billings. Okay, so I talked about global scale, about like city scale, but the rest of my talk, I want to talk much more about even smaller scale, like a building, like a school, like a hospital, and that's because, as Joe was saying in his introduction, that's the kind of stuff I've been working on a lot in the last 15, 16 years. So when we go really to smaller scale, what we want to have is really the structure of the contact network in which each node is an individual, a link will be a contact, so an interaction on which the disease can spread. And on that topic, there have been lots of advances in understanding epidemics on network from the purely theoretical point of view. And if you don't know it, I really recommend the review by Romualdo, Claudio, Peter van Megen, and Alessandro. But what was kind of missing is data. And you see this, this paper, I don't remember when it was, 2015, but it was still saying, okay, measuring contact networks is actually very challenging. And indeed it is. What I've talked to you about was using surveys. But as I said, with surveys you get a set of echo networks. Even if you ask the names, typically it will not be the name of other people who participated. So you can obtain contact matrices, which are once again extremely useful. With data from cellular phones, there also typically you can get an idea of collocation of people. You can say they were in the same area. Also with apps like Foursquare or things like that, you can say, okay, those people were in the same building at the same time, but then you need hypotheses about did they actually meet. So what can you do? Develop sensors and use sensors to detect the proximity of people who are wearing these sensors. An obvious limitation is that then you don't get the contacts with people who do not wear the sensors. Okay? It's just within a close population. And this kind of approaches had started, actually the pioneers were Alex Pentland and collaborators who developed this, their sociometers, but their goal was more to understand interaction in offices and how people would collaborate and the efficiency of, and to relate that to the efficiency of the work. Other projects have used Bluetooth between sensors or developed various types of modes or sensors in the context of schools, in the context of hospitals, or even in using smartphones in a university. So you had basically a bunch of, a series of groups that kind of, very often they did a one-off. They did one study and then that was it, in a specific context. So what we did with sociopatterns was, where we started in 2008, was to say, okay, we would like to obtain data that we can obtain relatively easily and that we can deploy in many contexts, because we don't want only to do one shot in like one school or one scientific conference. And this effort was led by Jean-François Pinton, who was at that time at the École Normale in Lyon, Xiao Katuto, who probably you all know, who is the scientific director of ISI Foundation, and Wouter Vandenbroek, who was a postdoc at ISI at that time. And by the way, all this came from drinking beers with Jean-François. So it's useful to have a beer with colleagues, especially if they are not from your lab and they are doing slightly different things, but you still have a common language. And so we devised, actually, so we used sensors that were already existing, but that Chiron managed to reprogram completely, and that are based basically on the emission of radio frequency packets at very low power, which allows to detect the contacts only when people were facing each other at 1 to 2 meters. And that was, and those sensors, I don't have them here, but they are very small, so you can wear them with like a conference badge, for instance. You can forget that you are wearing it, which is a good thing, and they don't cost too much. So we started deploying that in different contexts, and I will just want to give 2 examples of the data. For instance, that was data in a hospital in Rome, where, so it's a ward, it's a children's hospital, meaning that the patients are all children and they all have a parent, caregiver. And you have the nurses, you have the doctors, and one sees very easily that the nurses, that's not a big surprise, it had been seen by other studies before. The nurses are the ones who are really in contact with everyone, not in contact with each other, but also with all the different categories, while the doctors, they don't see the patient that much. And then you have a structure where each caregiver sees typically their children and not the other patients, which is good because you don't want the patients to risk to infect each other. So the doctors were actually quite happy to see that. And that's another data set that was collected in a primary school in Lyon, in France, and where we obtain data on which child was in contact with how the children met during the day that we collected during 2 days. Okay, so we have this kind of data, and it opens, it really opened a world to us, because first it was data we had collected ourselves, so we knew its limitation, we knew what it looked like, and then it was a temporal network. Suddenly it wasn't a static network, it was a network that was moving in time. And that, of course, opens many questions on how you work with temporal networks. So people had started thinking about that, but it was still a pretty open question. So you want to understand how to explore this data, how to represent it, how to extract interesting information, how to model, and what kind of processes, how processes on networks are impacted by the dynamics of the network. So we have done, so you can find, and also lots of this data also open, and either on our website or on Zenodos, etc. As Joe mentioned, we are actually extremely happy that so many people have jumped on those data and exploited them for their own research questions, because of course there are so many questions that can pop in the head of various researchers and who have different background, different ideas, and so that's why we were really, from the start, we wanted all this data to be open. So obviously, once you have this kind of high resolution data, you want to use them to inform model of epidemic spread. The question is, how do you do that? So first, we understood this, and the data from the school was extremely inspiring, and we used it a lot, also because schools are an important place for epidemic spread. But already, just looking at the data can suggest some strategies. For instance, we understood very early, and that's, you can say it's trivial, that there are more contacts within classes than between classes. But then you can quantify that. And in particular, you can say, okay, given this difference, it could be interesting when there is like a pandemic propagating around, instead of closing all the schools brutally, to say, okay, let's see if in a school you start having a couple of cases, let's look at which classes they are in. We just close that class, and the rest of the school remains open. I just want to draw your attention to the date, which is 2011. So it was much before COVID, but even at that time, in the literature, there were studies on whether closing schools was or not efficient. And for instance, it was already well known that during school holidays, the influenza, if the school holidays were in the middle of the influenza peak, it would delay a bit the influenza peak. So there was already the knowledge in the epidemiology literature that indeed schools were important and that it was a way to act on an epidemic. And so already just looking at this data, it gives you some ideas about what could be done. And in fact, at that time, so we acted on that by building a model in which we simulated basically a hypothetical scenario for an influenza pandemic. And we said, okay, let's look at what happens if I fully close the school with respect to if I close only those classes where I detect cases. And basically, so we built this agent-based model that was fed by the temporal network of contacts actually recorded in the school, so as realistic as possible, and that could indeed show the efficiency of this potential class closure. Obviously, when COVID arrived, the question emerged again, because if you remember, when COVID arrived, so I don't know which countries you are from, but in France and in many other countries, one of the first measures was to close the schools, okay? Not only to, so in France, if I remember correctly, they closed the school first, and then 1 week afterward, they closed everything. But that was really one of the first response. It was, okay, let's close the schools, the children are propagating a lot. At that time, nobody knew clearly whether there was a difference in spreading by children, by adults, etc. But obviously, everybody understood quite fast that it had a lot of negative consequences. I won't go into that. I'm not specialist, but it's just obvious. And so the question came: how do we keep the schools open to maintain education while still containing or limiting transmission? And there were, depending on countries, depending on the period, there were many, many different protocols put in place. Of course, masking, improving hand hygiene, improving ventilation, and closing classes or schools when you knew there were 1, 2, 3 cases detected. It varied, I mean, at least in France, it varied a lot depending on the mood of the minister, basically. And there was no clear evaluation of all these strategies, right? I mean, it was, okay, let's do that and see what happens. So modeling can help here, and that's what we try to do. We modeled the propagation of SARS-CoV-2 using the same kind of agent-based model we had before, which means fed by the data of temporal networks of contact collected in various schools. And then we could simulate various protocols, because what was very different with respect to what we had studied before was the asymptomatic propagation, the pre-symptomatic propagation, and the testing, because in 2014 there was no test to detect rapidly if you had influenza. Here we were lucky that we had the test to detect COVID very early, and so we wanted to simulate these various protocols and to understand which was more efficient, at least in this model. So we used data that we had collected over the years describing the contacts in a primary school and in a high school to have some diversity. And we considered various protocols. The first, of course, when a child has symptoms, then you test and you identify COVID, you quarantine. But then we added what was actually done, in particular in France, was if you detect 1 or 2 cases in a class, then you quarantine just that class. So you close the class, as we had suggested in the simulation with influenza. Or maybe you just screen the class for COVID and you just isolate those students that were positive. And we compared to a radically different approach that had been advocated in other countries, and that was actually, I think, used in some other countries, which was to test regularly all students on a voluntary basis at a certain frequency, and even if you don't have cases in the school. That was because we knew at that time, people had started to understand that there was a lot of asymptomatic cases and that there was pre-symptomatic transmission. So the idea was, okay, you test everybody, the people who are positive, even with no symptoms, you ask them to isolate and do not close the class. And what we found out is that, so here I show the, on the y-axis, you have the fraction of cases that are avoided by the various protocols. On the x-axis, you have the various protocols. And the ones that were implemented in France were only reactive. So they were useful, they were avoiding cases. But if we had been able to do regular testing, even with just 50% adherence and one test per week, it would have been better. And the reason that any reactive protocol had strong limitations was just because you can propagate without symptoms. So when you start detecting cases in a class, in fact, it has already propagated to other classes. Okay? So the regular testing would have been a better strategy to avoid cases, and in fact, it would have been a better strategy as well to limit the closure of classes, because you were isolating only positive cases and not closing whole classes. Of course, I mean, that was actually not implemented in France, apart from some experimental testing in a few selected schools. That's a policy decision at some point, because obviously doing regular testing systematically every week, for instance, it has an organizational cost. And so you have, of course, to decide where you want to put your testing ability. So that's also a decision that has to be put in balance with other factors. In any case, we were quite happy that our results were actually taken by the Scientific Council on COVID, and the advice was to do this regular test. Now, after doing these studies, I wanted to take a step back, because what did we do? We did something very usual, in fact. We have the reality, the real world. We collect data from that real world. We represent that data as, in that case, with a temporal network. We do a model of propagation, we obtain results, and we give some policy advice. However, first, you don't always have high-resolution data. That was our case for school data, but there were in 2 or 3 schools. It was not, generalization to all the schools in France or in other countries. In various cases, you have various data sources, you have various levels of description of the data. For instance, you could have only the class schedule, so you know which students are in class at the same time in the same room, but you don't know the specific contacts. And so you want to know, okay, then what our results say is that some protocols are better than others. Now, if I had done the same study but with different data, would have I reached the same conclusion? That's pretty important. That, I mean, it's theoretical, but it's still quite, I think, also important in applications. So let me to ask 2 questions. First, if I have measured, let's say, the same reality in 2 different ways, so I have 2 different data representation. One is very detailed, and the other, as I was saying, I just have the class schedule. and I feed my models, will I get the same results? Will I have the same policy advice? And other question, if now I measure the same reality, but at some other point in time, or if I measure a different school, for instance, then I have two data sets, I feed them in the model, will I get the same results? What is the robustness in the sense of my results? So first, let's consider the fact that I have these data sets that describe the same reality at the same time, but I don't always have the same data resolution. So what I do to understand what's happening is I will take in fact, the data representation at the highest resolution, and I will represent it in a coarser way. So I will fake that I have less high resolution data. And I can do that in various ways. For instance, I can still assume that I know the network of contact, but from a static point of view. So I forget about exactly when the contacts happen, but I keep the information on the fact that some people interacted for a long time and some others did not see each other. Or I move to like a contact matrix representation in which I forget the information about who exactly met whom. I just know that on average, let's say in a school context, the average time of contact between a child or a student of a given class and a student of another given class, I know that. Okay, so I know the structure globally, but I don't know the detailed interaction network. And then there are some other refinements. Then I can feed the model of spread and protocols with these various levels of data, with these various levels of resolution. And what we had actually already looked at much before COVID was the case of no mitigation measures. What happens if you have a spread in a population and you have different kind of information on the structure of contacts? What we knew is that you will typically, if you have coarser information, so less detailed, you will overestimate the epidemic size. But if you rescale some parameters of the spread, then you will obtain very similar epidemic curves. But that was just, unmitigated spread. That doesn't tell us anything about whether the protocols will act differently. Those protocols, they are really okay. There's one person who is tested positive, and I isolate that person. So if I have a network, it means no contact with the others. If I have just a matrix of average contacts, maybe it's much less important. So maybe other protocols will work better. Who knows? So we did that by going back to the modeling of a COVID-like disease, agent-based, with these various protocols and in various contexts, so workplace or schools, and so with reactive quarantine, with regular testing, also with telework for the work context. And what we obtained was actually a very good news, in my opinion, that if I look now at which protocol is the most efficient, if I look at the order of efficiency of the various protocols, I always get the same, whatever the data representation. So it means that, on the other hand, there are differences in how efficient those protocols are. If I want a specific number, then it's much less, so it's more dependent on the kind of data I'm using. But if I just want to know what is the best strategy, then I'm safe. So that's, in my opinion, a good news. And it gives, let's say, some confidence to the step, which is very delicate, of translation of numerical results into policy recommendation. Of course, there is still a limitation. For instance, if let's say the policymakers tell you, I want a protocol that lowers at least 20% the epidemic size, and if I do the simulation, I get 19, maybe I'm not sure it's over 20, or I got 21, sorry. I'm not totally sure it's not, in fact, 19 if I had different data. So one has to introduce, to take into account the uncertainty, and maybe to try to convey this message. But at least which protocol is the best did not change. Now, more complicated question, and which I don't have really an answer. If now I take data at two different moments or two different schools, how do I get the same results? So the problem, so we did these studies with two different schools in different, with students of different age, and we obtained the same results. But in general, we have, and even there we had one data set for primary school, one data set for the high school. So how do you get more data sets? You can do other measures, of course, but it will be at another moment. It's not obvious, maybe it's a different context. And also, one thing I carefully hid was, in fact, the data we have are typically a few days of data. Now, the simulations we do are about like 15, 20, 30 days. How do we do that? Okay? How do you transform your very limited data into something long enough to test to feed into the models? And how to get more realistic data sets without additional data? So, to do that, what you do is you build what are called surrogate data sets. And I will just show you quickly two ways we have. There are many ways to build surrogate data for temporal networks, but I will show you two papers we've done recently. In the so first, in the context of schools, we have a few days, and we have on these days the detailed timeline of contacts on each pair of individuals. The simplest way to extend temporally is just to repeat the data timeline. Okay, that's very simple. However, and we had checked that already in a different context long ago, it can bias the simulations, because you have links that are repeated. Like if you have just one day of data, every day is the same, so you contact the same people every day, which is not realistic. And so you might have various effects. Actually, the repeated links, they favor the propagation locally, but in reality, you are a bit more random than repeating everything the same day. And so it creates, being more random creates more propagation path. So it's there's a trade-off, and it's unclear what happens. What we propose in that in this recent paper is to say, okay, we have data of several days, so we can first look at which pair of individuals meet each other like every day, and that we claim it's linked to friendship. Not necessarily, but we call them like that in the school for simplicity. Then we built synthetic data in which we put a certain fraction of those friendship links to be repeated, and then we add other links a bit more at random, but in a way, let's say, to respect the statistics of contacts between classes. And we have a couple of parameters that we tune so that basically what we reproduce is the proportion of contacts from one day to the next that are the same and that are random. So basically, from one day to the next, the people you meet, how long you meet them, is in part the same, in part changing. And we try to reproduce this partial repetition, partial random that we observe in the data. And then we have a baseline in which we don't take that friendship links into account. We just do random from one day to the next respecting the class structure. So we have like 4 days of contact, and we built synthetic weeks on which we can simulate the disease as long as we want. What we obtain, and that just to illustrate, is that when we repeat the data, so it's this plot, so that are the distribution of epidemic sizes. Basically, if we repeat the data, we have a small probability of small outbreaks, so basically we favor the propagation. And in the 2 other cases, we have something quite similar. We have small differences. I won't go into the detail, but what's important, I would say, is that if we look now at the spreading patterns in the population, obviously, depending on the way we use the data, we build this data, at the individual level, we will have differences. But let's be honest, spreading patterns at the individual level in a school, anyway, if you want to simulate a different school, the identity of individual is not the same. So what might be more interesting is, do we have the same spreading patterns at the class level? So which class will be infected first, second, etc. And that is very robust, basically whatever repetition or more involved surrogate data building method we use. So that's pretty robust. Another way, which is totally, I would say, not perpendicular, but it's very, very different inspiration to build surrogate data, just want to mention it because we just got it accepted, is you take whatever temporal network and you want to build another temporal network that is similar. And in similar, we mean similar statistics of whatever thing you measure, whatever property you measure. And if you simulate dynamical processes, spreading, but not only, maybe opinion dynamics, etc., on the original and the surrogate, you obtain similar results. And to do that, we used a method put forward by Giulia Cencetti, which is to basically decompose your temporal network into small building blocks, which are called egocentric motifs, which basically tell you for each individual what is its neighborhood for a small time, for a short time. And then you have your initial temporal network. It's like you unmount it, and you have lots of pieces, and then you put them back together, trying to respect a certain number of features. And if you do that, basically you can obtain surrogate temporal networks of any duration, because you can continue building, gluing together and expanding in time. And potentially, we are working on that. You can even do that and expand your data set to represent a population which would have similar contact patterns, but of a different size. I won't really have time, or I can do that maybe in a few minutes. Do I have 5 minutes? A reverse question I wanted to discuss briefly was, so until now, we've looked really at the data on the network and understanding how the information on the structure of the interactions can change the conclusions and how to deal with high resolution data, how to feed epidemic models. But the reverse question is, now let's assume I know the network on which we have a propagation, but maybe the process itself, the parameters of the disease, I don't know them very well. And if you look at the literature, there are many papers on, for instance, identifying important structures, important nodes on the network using very simplified models. And I myself submitted some of those papers. So you use typically an SIR with very arbitrary parameters. You say, okay, I've shown that this structure is important. Yes, you've shown that, but with a very simplified model. If now I have a more realistic, a real, let's say, disease, will that be true? And to investigate that, we looked at the propagation patterns of a disease on a network that is defined basically as a matrix Cij, which is just the probability that in my numerical simulation, node I will infect node J. I can use many different, I can take a network and I can use many different models with many different parameters and build these infection patterns. And then I can look, say, okay, are those patterns similar or different depending on the disease parameter? While usually you ask the opposite. You ask, what are the properties of the network that change the infection parameters? So now I have a given network. I do many different, I use many different models. And what we obtain, so here we have a bunch of models starting from SIR. I'm going to Markovian, non-Markovian processes, a COVID-like model. They all unfold on very different time scales, but we obtain that the propagation patterns are extremely similar. They still depend a bit on R0, but not too much. And that is also very reassuring, because if you look with, if you use very simple contagion models, very simplistic, you can still understand which structures will be important in a much more complicated spread. So in that paper, we've done that also with complex contagion. We've done much more, but I just wanted to put that here. And finally, I want to end with a short perspective, which in my opinion is one, extremely important and will grow a lot in the next years, which is to take into account the changes in behavior that are induced by the spread of the disease itself. And the question here is really about data, because the idea that because there's something spreading around, you will change your behavior has been there for ages. But most of the models which have been developed were based on extremely strong hypotheses, because we don't have data basically on how people will react, both in changing their contact network, in adopting protective behavior, etc. And that is currently evolving in terms of not having data. Thanks, for instance, to the comic survey I was mentioning before, we start having data not only on the contact patterns of individuals during different periods of the COVID propagation, so with various levels of restrictions, but also we have data on the perception of risk by individuals and its link with contacts. So it means it's possible to divide the population not only along the age dimension, but also along the perceived risk with respect to the disease. So you can say, for instance, in the group of people who are between 20 and 29 years old, there is a fraction that considers they have a strong risk, low risk, etc. And then you create generalized contact matrices that give you the number of contacts, the average number of contacts between different groups, and you can feed that to a model. And here I don't want to enter into the details. What I want to show is that we have a model in which we can add, we can introduce data linked to behavior and risk perception, but we still have to make a lot of hypotheses about how the behavior is changed, because not only of the risk perception, but about the evolution of the epidemic. And for instance, here we made the hypothesis that people are more likely to reduce their contacts if there are a lot of people in the hospitals, and they are more inclined to relax their behavior if there are more people who are vaccinated in the population. So, relatively simple hypothesis, reasonable hypothesis, but on which we don't have data. And I don't want, once again, to show you any results on that. I just want to say that this model is still only partially data-driven, and it still has a very strong hypothesis, which means that we really need more data, which actually, in my opinion, needs to be addressed both at the large scale by surveys, in anonymous surveys where you obtain statistics at the large scale, but also we need probably to interview people to understand better how they react to changing in the environment, in the spread of epidemics, in the information about the spread of epidemic, etc. So I will finish by that, and I want to thank all the collaborators I have had in this last years about these topics, in particular Vittoria Colizza from INSEM and all her team, Gio Cattuto at ISI, with whom we started this fantastic adventure of social patterns, Daniela Paolotti, with whom we did this last work on behavior, and Giulia Cencetti, who was a Marie Curie postdoc in my lab, Diego Contreras, who was also a postdoc, and Alessandro De Gaetano, who is currently finishing his PhD. And obviously, I want to thank Jacopo and Giovanni for allowing me this fantastic parenthesis in London. Thank you, guys.
I must say that Jacopo did all the heavy lifting for this. Questions? Anybody?
Thank you for that presentation. I was wondering, so basically, in some sense, if I understood correctly, you are saying that you can take these models at different resolution, sort of very detailed, less detailed, but if you do this in a correct way, then at least qualitatively, the results are going to be very similar in terms of final epidemic size, which control measure is the most efficient, so qualitatively. But what could you say something about the inference? Let's say that now you want to actually infer some parameters from a real epidemic, and then which model are you choosing, and what might be the implications of that? So if you actually want to infer epidemics in real time and you want to forecast, then because what you have done here, it was more like almost like a post hoc analysis kind of thing, rather than in real time, so to speak.
Well, if you're in real time, you want to go to a simpler. So I think since it's like various effective representations, and in some you have much more parameters than in others, you'd better go to a simpler one. Right? I mean, if you want to infer the whole structure of the network, that's more complicated than inferring the contact matrix. And I've grown up with networks, but in fact, during the COVID crisis, people were using contact matrices, not networks. Because that works, and you don't have information on the contacts. On the other hand, more recently, the work by Vittoria and her team that she showed me on Mpox, they're using network concepts. Because here probably you really need that, because you have very heterogeneous degrees. So it might depend on the specific question. For instance, there are purely network effects cannot be seen by contact matrices. Now, do we have a population where you have very strong heterogeneity or not? In a school, you don't. In an office, you have heterogeneity in the time spent, but it's still pretty dense locally. So the representation by contact matrix is not that bad in a certain number of contexts. So it's probably, those results are probably not as general as I pretended them to be.
you please comment briefly about the cases where the homogeneous mixing was actually doing better than more complex representations in some scenarios? I couldn't really very fast on that one. I think it was for the primary school data.
So no, it's not doing better. Oh, here. No.
No, before. Yeah.
No, homogeneous mixing is not doing better. It's telling you, it's giving you the same answer than the others. And the actual level of, so the fraction of case reduction predicted by the various data representation is different. So here, the homogeneous mixing would underestimate the effect of the measure. But in some sense, we don't have a ground truth because we never measured that. In fact, so what we know is that we have data that is representing the school at a certain moment in time. And if we do the simulation with this very detailed data, it gives us an answer on how good the protocol would have performed. And now if we say, okay, I just have an average number of contacts, and I do a very simple homogeneous mixing, I will get another number. But then if I simulate another protocol, then in both cases, the answer will be lower. Now, there are some protocols that would be very difficult to simulate if you don't have a network, like contact tracing, like digital contact tracing. I'm not sure how to do that if you don't have an underlying network. Well, fully mixed is, you can still say it's a network, but then your contacts would be the whole population, so it becomes irrelevant.
Any other question? Yes.
Could you just speak a little bit more on, at the very end when you're talking about the behavioral aspects of this, could you just speak a bit more on, what would the ideal data set look like? Like, especially being post-pandemic now, right? Yeah, right. So if you could read people's minds.
We're writing a project right now in which we propose to do some surveys. One very delicate aspect is, so actually you need two things. First, you need to ask people their contacts, and then you need to ask them their behavior and their perception of the risk, and another bunch of potential drivers. And then you have to identify the drivers of, let's say, behavior change among the socioeconomic, age, gender, etc., all the other variables. So you need like a kind of regression to identify that. And then you want to stratify your contact matrix according to age and that driver. The very big problem is that typically, let's say this, if this driver is a variable that is, let's say, simple, then you can ask people about their contact, and typically you ask the age and gender of the person they have contacted. But they don't necessarily know this other variable, this other feature. And in the study we did, because this other driver is risk perception, we had to assume a kind of locally homogeneous mixing, in the sense that if I know the age of the other person contacted, I will just attribute to that person a risk perception that is statistically taken from the distribution in that age group, because I don't know. And people will not know everything about the people they have contacted. So it means that, and there's been a paper by Nicola Perra and collaborators, about generalized contact matrices in which they show that it can influence the fact that you have or not assortativity along that other feature that can influence the spread. And that's probably the most difficult point to obtain this kind of data. So that's where I think detailed interviews could help. Because then you can try to understand more deeply for some people, as many as possible, if they tend to associate more with people who have the same kind of beliefs, etc.
Have any other questions?
Yeah.
I think we can all go get a beer and help me thank our speaker again. Alan is going to be around until Friday morning. Anyone who wants to pop by and try and have a chat. And I think we're moving to the Dickens, at least for a pit stop.